of the country, not only on the national but also on the global stage. As time goes by, Technovanza has effectively progressed towards its goal of taking technology to the society by meritoriously passing on the flame of expertise to light more torches. Technovanza has always been a proficient and prime platform in enlightening the young minds of the country. This COVID pandemic may have forced us to stay at our homes, but nevertheless, that didn't stop us from conducting online guest lecture series in the years 2020 and 2021. Previously, we have been graced with the presence of some of the world's eminent personalities and pioneers of diverse fields, including Dr. APJ Abdul Kalam, Mr. Ratan Tata, Mr. Kartikeya Vikram Sarabhai, and many others who have lavished light on bright juveniles, thus guiding them to new areas of interest. With sheer bliss, I am thrilled to inaugurate this lecture by adding an incredible gem to our star-studded list of dignitaries. Now, I would like to introduce our guest today, who is an amazing atmospheric scientist and former research scientist at NASA's Ames Research Center. He has helped conceive, developed, and led 10 NASA airborne field missions, the effects of aircraft on the atmosphere, the role of clouds in Earth's climate system, and has been involved in many numerous satellite missions for both Earth and the planets. He is not only a great professor, but also is an inspiration to several generations of humans who wish to live on a safe and healthy planet in future. Today, I am pleased to welcome the prodigious Mr. Owen Brian Toon to our very first guest lecture series of the year 2022. Mr. Toon is currently a professor in the Department of Atmospheric and Oceanic Sciences and a research associate in the Laboratory for ASPU of Colorado. He was founding chair of the department, which led the CU to be ranked as the leading university for atmospheric science in the world for 3 consecutive years. He also received an AB in physics and is also a PhD in physics. Owen Toon, sir, has published more than 350 papers in referred scientific journals. He received NASA's Exceptional Scientific Achievement for the studies of the climate of the Earth and the planets, and of the ozone hole as well. He and his colleagues won the Leo Szilard Award for Physics. Sir, this small introduction wouldn't do enough justice to the outstanding achievements you have earned in your profession. You have harmonized hard work, patience, perseverance, and intelligence in an excellent way. We are truly honored by your presence today. We also have with us the Dean of Student Activities and Alumni, Dr. Rohin Daruwala, sir. Sir, I request you to kindly say a few words.
Good morning, Professor Toon, and good evening to viewers in India. It's my pleasure to welcome Professor Toon to the guest lecture series at VJTI. Over to you, Professor Toon. Thank you for visiting VJTI online.
Well, thank you for inviting me to speak to you.
Our pleasure. Continue, sir.
Okay, are we ready to...
We'll have a Q&A session after the lecture. So please leave your questions in the live chat below. So without any further delay, let's be a part of a mind-blowing talk under the guidance of Mr. Owen Brian Toon. Sir, handing it over to you for the lecture.
Thank you. Let me share my screen. Okay. Oops. Let me just go again. We're going to have a few problems with the overly delicate machine here. Well, good evening, and thank you for inviting me to talk to you. So today I'm going to talk to you about the extinction of the dinosaurs and nuclear wars. So what this is about is the climate science of stratospheric black carbon. But you might be wondering, what does the extinction of the dinosaurs have to do with nuclear conflicts? And there's really two reasons why I'm linking these two subjects. The first one is that I found in speaking, at least in the United States, that if I talk about nuclear conflicts, no one will come to hear the lecture. It terrifies people to think about it, and they would rather not think about it. On the other hand, everyone's been interested in the death of the dinosaurs since they were children. And so they have no empathy for dinosaurs because they've been extinct for 60 million years. So people will come to hear about that. But the more important reason is that I think there are strong parallels scientifically between the extinction of the dinosaurs and nuclear conflicts. And so the question I really pose to you in this talk is, if we had a full nuclear war, or even a nuclear war between smaller nuclear states like India and Pakistan, would we face extinction? Would a large fraction of the population die, as the dinosaurs did? So let's talk about the dinosaurs first. See if I can advance the screen. So there are many mechanisms that have been proposed for the extinction of the dinosaurs. Most of them have no data to support them. So this cartoon by a cartoonist named Larson has always been my favorite explanation. The real reason dinosaurs became extinct is because they started smoking cigarettes. So I like this one for two reasons. First of all, it wasn't just the dinosaurs that became extinct. 75% of the species that we know about on the planet became extinct. Lots of them are like plankton, which could have never smoked a cigarette. So that's an implausible theory. Plus, we can test this theory. It's there are no cigarettes left over from 66 million years ago. So this is obviously not a good theory, no data, and it doesn't explain the whole problem. The explanation really was found by the Thelvarez family. So on the right of this picture is Walter Thelvarez in the blue shirt. He is an alpine geologist. He studied the mountains in Europe. And his family has a summer house in Italy. So he was visiting there in the early 1980s. He was bored and he wanted to find some way to escape his family, probably. And so he discovered that there were some paleontologists working in Italy in a town called Gubbio. So he made friends with them and asked if he could do something to help them in the summer as a summer project. And of course, the paleontologists thought, well, this is annoying to have this guy here bothering us. Let's see what we can do to get rid of him. So they said, go over to this rock and you'll see this thin layer. So on the left, my finger is pointing at the layer. This one, this exposure is in a state park in Colorado where I live. And Walter's hand on the right is on the layer in Gubbio. And so Walter contacted his father, Louis Thelvarez, who was a Nobel Prize winner in physics for inventing the bubble chamber, and said, what can we do with this? And they knew that there is a constant influx of micrometeorites to the Earth. About 40 tons of microscopic particles fall onto the Earth every day. And so they thought, well, we'll see how many of these particles are in this layer by looking for iridium. Iridium is an iron-loving element, which means that when the core of the Earth formed, the iridium moved to the core, and so it's depleted in the crust. So they expected to find iridium from the micrometeorites in this layer, and that would tell them how long it took the dinosaurs to become extinct. To their surprise, they discovered that the layer contains huge amounts of iridium, and therefore it did not represent many, many years of a casual, small influx of micrometeorites. Instead, it was a result of one single large asteroid collision, which they thought came from an asteroid about the size of Mount Everest. plunging into the earth at the speed of 10 times that of the fastest rifle bullets. So this is an incredibly energetic event with about an energy of about 10 to the eighth, 100 million megatons of energy. So the clues to how this caused an extinction are found in this little layer, which is only a few millimeters thick over most of the Earth. So here are some of the things we find in this layer that are relevant. At the top, there's a pulverized target material. And this is a grain of quartz. And it's being examined under a polarizing microscope. It's about the size of a few hundred microns, a grain of sand. And these little layers here are shock layers. So this grain of quartz was heavily shocked. And people have found that the only thing it can cause this on the Earth are collisions of asteroids. And so this is strong evidence that this was not a volcanic eruption that they were looking at, but an asteroid collision. The next thing that's in the layer are spherules like these. So these things are obviously melted rock that came from the impact site and from the asteroid. There are about 10,000 of them per square centimeter on the surface of the Earth in places where the layer is exposed. So I'll come back to these in a minute because, well, let's talk about them now. These things were probably entered the Earth's atmosphere like shooting stars. So I'm sure all of you have seen a shooting star about once every 10 minutes in a normal day. You can see them at night. And in a meteor shower, you might see one every minute or so as a bright streak of light flashing across the sky, which is when a sand-sized grain of asteroidal material or cometary material enters the atmosphere, and friction slows it down and heats it up until it evaporates and leaves behind a glowing trail. In this case, we don't just have a single shooting star. We have a huge quantity of them coming in over the entire sky. So the entire sky flashed up into a glowing region, a few thousand degrees Kelvin, because of the heat from friction in the air between these shooting stars and the air. So the whole sky was glowing. It would have looked something like a sheet of lava seen from a distance, but probably the distance was about 60 kilometers above the ground. So this didn't burn things directly. However, the intensity of this light was so high that it would have ignited materials on the ground that were like leaves and fine branches, easily ignited materials. And there's evidence in this same layer that, in fact, most of the material on the surface of the Earth burned. So this next slide is elemental carbon. So these are small spheres of elemental carbon, black carbon we call it. They form fractal particles. And these are commonly seen even after normal forest fires today. These have the same size as normal forest fires on the Earth. And so as far as we can tell, the entire surface material on the Earth burned. There are probably other things in this layer. There are probably small dust particles left over from asteroidal material that did not condense. So we think the origin of these spherules, the asteroid hit the Earth and the asteroid was vaporized, and a similar mass of Mexico was vaporized. The asteroid had a volume of about 600 cubic kilometers. This is an immense amount of material. So that vapor rose above the surface of the Earth, probably thousands of kilometers, and then fell back toward the Earth and re-entered the atmosphere over most of the planet. Some of it probably didn't condense to form these spheres, and it's probably left as little particles. And we know that we can see that they're there because we can detect iron particles that are nanometer sizes, We haven't been able to quantify that. And there's probably also a lot of sulfur there because asteroids have a lot of sulfur, and the target area in the Yucatan Peninsula of Mexico where it hit, where there's a huge crater, one of the biggest craters on Earth, about 200 kilometers across. There was a lot of sulfur in that material. Some people think the sulfur was important to the extinctions. But what likely happened to cause the extinction of the dinosaurs is that the glowing skies from all these shooting stars simply broiled them alive. There were very high radiant intensities just from black body radiation from all this material, which had an optical depth of around 8 or 10. So if the spherules hadn't been hot, it would have been pitch black. So I tell people you can do an experiment at home if you want to see what happened. You can go to the grocery store or maybe your yard and get yourself a dinosaur. Not all those dinosaurs became extinct. The avian dinosaurs did not become extinct. So you can go get yourself a chicken or a turkey and take it home and open your oven. And most ovens have an oven setting and they have a broiler setting, at least in the United States. I assume it's the same in India. The broiler is a glow bar at the top. And if you put it on broil and throw the dinosaur into your oven and let it cook for an hour or two, you'll find that it's badly burned. And that's probably what happened to most of the dinosaurs. So this is not like the sun, which is a point source where there are shadows. Instead, this is the entire sky is glowing red. There were no shadows. There was no place for the dinosaurs to hide. And therefore, any large creature that didn't have a hole or a cave to hide in was probably burned alive. That's, of course, not all that happened. From all this smoke, there was very little light that was allowed to reach the surface. So this graph shows the transmission of light through the atmosphere as a function of the optical depth, which is a technical word telling us how much light absorbing or light scattering materials in the atmosphere. It's not too hard to find the optical depth. There's several different ways to do it. But the back of this car shows dust. It's fallen on a car. It's not my car, but sometimes my car looks dirty like this, too lazy to wash it. And you can see if you scrape away the dust that you can see through it. And so each layer of particles is about 1 optical depth. So we can count the number of layers of particles and find out how many optical depths there were. And so, for example, this specimen here, you can see some of these spherules in it, and the layers of black carbon are in here, and you can just count them and give the optical depth. So the optical depth of the smoke is around 100. Here's a transmission of light through that. 100 comes down here somewhere. Very little light, if any, was coming through this layer initially. So what caused the extinction in the oceans? On the land, the extinctions are mostly caused, as I explained, by this burning, most of the biota on the land. But in the oceans, nothing is going to burn from that. But there was a mass extinction in the oceans. For example, this creature here was like a modern whale shark. It ate plankton. It swam through the ocean with its mouth open, filtering out plankton on these gills. And so the important point about this is that plankton could not reproduce without sunlight. So this is an interesting thing. On the land, there's a food pyramid. There's a huge amount of food at the base of the food chain in the terms of trees and grasses and plants. And then there's herbivores that eat them, like cattle. And then there are carnivores that eat the cattle. Where I live in Boulder, Colorado, the top of the food chain is mountain lions. Probably in India, it's tigers. But it takes about 10 years for the tigers to eat everything below them and to consume all the plants. So there's a lot of food on the land. Even following a burning of all the trees at the surface, there was still food in the subsurface like roots and insects. But in the oceans, there's a food rectangle. So the phytoplankton have about the same mass as the zooplankton and the fish. And so the phytoplankton have to keep reproducing constantly to supply the carbon in the oceans for the food chain to run. It only takes about 10 days to consume all the food in the oceans in the food chain. 10 years on the land, 10 days in the oceans. So if the phytoplankton couldn't reproduce because of the lack of sunlight, the food chain in the ocean collapsed, and the animals and zooplankton that lived in the surface waters and used used light to eat, many of them became extinct. On the other hand, in the deep ocean, where the life is based on eating dead material floating down from the top, that life survived. Of course, if you make it very dark at the surface, it's going to get cold very quickly. And these are calculations using the National Center for Atmospheric Research in the United States climate model of the surface temperatures following and all this smoke in the atmosphere. There's about 15,000 teragrams of smoke in the atmosphere, 15,000 million tons of smoke. So we can see in this graph at the second year after the asteroid impact that the red and yellow colors are above freezing, the green colors are below. So all the land had temperatures below freezing. And at the time it was warmer than now. And so there were dinosaurs living in Antarctica. So these creatures were not used to cold temperatures like this. And if any of them survived the burning of the forest, the cold temperatures probably would have killed them. And of course, it was also pitch black. So if you were a large creature and you were trying to hunt in the dark, it would have been very difficult to find food. So these things caused the extinctions. How did our ancestors survive? So sheltering was an important survival mechanism. So people have studied who survived, what animals and plants survived. And our ancestors are small creatures mostly. There were some dog-sized creatures, but they were mostly small creatures like this guy, a shrew. And they lived underground. They were probably nocturnal, good way to avoid being eaten by a dinosaur. And they were able to just go into their holes and survive the forest fires, just like modern rodents do in a forest fire. They don't try to run away from it. They go underground and hide. And of course, there was lots of stuff underground to eat, from roots of plants and insects. There were also creatures like this ancestor of the avian dinosaurs. Probably if you lived in a termite mound like this, you could hide from the fires. And a lot of the avian dinosaurs seem to be to live in swamps or areas where there was a lot of water near the coastlines. They probably just hid in the water until the fires went away, and then survived probably very difficultly on things that lived in swampy areas that may not have burned. So those seem to be the survivors. A very interesting thing about the evolution of life on Earth is that it seems to get stuck in unproductive forms. So up until about 600 million years ago, the life on Earth was blue-green algae and very simple single-celled creatures. Then there was a flourishing of multiple-celled creatures and more advanced life. About 250 million years ago, there was a mass extinction event, not due to an asteroid as far as we know, that led to the rise of dinosaurs. And around 200 million years ago, the dinosaurs became the dominant species after another mass extinction event. Mammals were on the Earth for 200 million years, just like dinosaurs. 200 million years. Mammals were unsuccessfully competing against the dinosaurs. We were hiding out in holes. There's no evidence that mammals were becoming dominant over dinosaurs. It was just the dinosaurs died and we took over. So it's interesting to think about, if this asteroid had not hit the Earth, who would be the dominant creature on Earth now? So a Canadian paleontologist named Dale Russell thought about this. And this creature in the back is a Trudon. He's about the size of a turkey or a pheasant, a large pheasant. He was one of the smartest dinosaurs. He had a brain to body size about the same as an armadillo, or maybe a pangolin. Probably not a very bright creature, but Dale thought that over time, this creature would evolve. He was already near bipedal and had hands like arms he could use, and nice advanced vision. So Dale thought that this creature would evolve from this one, which would have been very handy for cartoonists. I don't know if you like cartoons in India, but in the United States, there's lots of cartoons, and the creatures in cartoons, the humans are always pictured with 3 fingers. He imagined this would have a belly button because it would have live birth, unlike dinosaurs, which mostly laid eggs, because he thought the large brain size would require that to produce a creature from birth. Of course, many people think that there's no necessity for life to have evolved to something that looks kind of human-like. And they said, well, this just looks like Dale Russell. And who knows what would have really been here. So that's a very interesting question. All right, let's turn now to nuclear conflicts. So this is a graph representing the number of nuclear warheads on the planet since the Second World War in 1945 up to close to the present. And you can see the total number of weapons maximized in about 1985 at around 70,000 nuclear weapons. Of these, there are 40,000 or so in Russia and around 30,000 in the United States. So something happened right here to cause a reduction in the number of nuclear weapons. It's become confusing in present time because current treaties no longer deal with the total number of weapons, and instead they deal only with the number of deployed strategic nuclear weapons. So by treaty, Russia has 1,700 and the United States has 1,700. There's another thousands or more, as I'll show you in a minute, in other countries. But in addition to that, they're allowed to have another 2,000 each weapons in storage. So they each have about 4,000 weapons they could use. In addition, they have a number that are being dismantled. So an important point is, why did they start being reduced? And the point I'm trying to make to you here is that politicians occasionally pay attention to scientists. So these are comments that were made by Presidents Reagan of the United States and Gorbachev of the Soviet Union, who reached a treaty to reduce nuclear weapons. Excuse me, and every American president since Reagan and every Russian president since Gorbachev has continued to reduce nuclear weapons. So what Gorbachev said in a speech after the treaty, which was in 1986, models made by Russian and American scientists showed that a nuclear war would result in a nuclear winter that would be extremely destructive to life on Earth. The knowledge of that was a great stimulus to us, to people of honor and morality, to act in that situation. So he listened to Russian scientists. Ronald Reagan said, he said this before the treaty, a great many reputable scientists are telling us that such a war could just end up in no victory for anyone because we would wipe out the Earth as we know it. And if you think back to natural calamities, back in the last century in the 1800s, volcanoes, we saw the weather so changed that there was snow in July in many temperate countries. And they called it the year in which there was no summer. Now, if one volcano can do that, what are we talking about with a whole nuclear exchange? The nuclear winter that scientists have been talking about, it's possible. Science can influence politicians. Politicians pay attention to the scientists in their countries. All right, India and Pakistan have powerful nuclear arsenals. This is a Pakistani aircraft. originating from the United States, an Indian missile. Both Pakistan and India have nuclear capable aircraft, which are dual purpose. Both India and Pakistan have ballistic missiles. India has missiles that can be launched from ships. It has a nuclear submarine that can launch missiles. And both countries have indigenous cruise missile programs. So these are very sophisticated militaries, they're very sophisticated weapons. They have large numbers of nuclear weapons. So this is a number of weapons in various countries outside Russia and the United States. So Russia and the United States have about 90% of the weapons. You can see Britain, China, France, Israel. These countries have somewhere around 250 weapons. Israel may have fewer, it's hard to tell. Pakistan and India are rapidly building up their arsenals. They currently are thought to each have around 150 nuclear weapons, and it's projected they'll each have about 250 nuclear weapons in the middle of this decade. Why do these countries have a number of weapons that are around 250? None of them have explained why they have the number of weapons they do. None of them are controlled by treaties, so there's no treaty obligation to have these numbers of weapons. But probably it's because they've counted cities. So the United States has about 300 cities with more than 100,000 people. Russia has about 200 cities with more than 100,000 people, 500 cities. Why did Russia and the United States ever need 70,000 weapons to attack 500 cities? Even today, Russia and the United States can attack every city in each other's countries with about 9 nuclear weapons, every city with more than 100,000 people. There are only 60 cities in Pakistan with more than 100,000 people. There's about 450 in India. So probably this is why Britain, France, China, Israel, Pakistan, and India are picking numbers like this, because that's all you need to attack every city in the countries you're worried about. Okay, so we can talk about the destructive power of nuclear weapons. People know a lot about this because of Hiroshima and Nagasaki, where nuclear weapons were dropped in the Second World War by the United States. But they also know about it because there were 500 nuclear weapons tests above ground. So this building in the middle here was very close to ground zero, where the bomb exploded in the atmosphere above it. It's an exposition center left over from an international exposition. It's still there as a memorial. And you can see all the territory around this was reduced to rubble. And part of this was because of the blast from the nuclear explosion. But mostly this destruction was caused by a giant fire. So a nuclear explosion is like bringing a piece of the sun down to the surface of the earth. There's a bright flash of light that only lasts a few seconds, but is so intense that just like the shooting stars killing the dinosaurs, it can ignite everything that's easily ignited nearby. And of course, the blast waves from the explosions knocks over buildings, and inside people had fires from stoves and things like that, which burned other parts of the buildings. Some of these concrete buildings here did not get blown down by the blast wave, but they were still totally burned in the interiors. So their interiors caught fire and burned. We can tell how many people will die in nuclear explosions in various countries. So we don't know what the yield of Indian and Pakistani weapons are. India tested a weapon with about a 40 to 50 kiloton yield in 1998. Pakistan tested weapons that were more like the yield of the Hiroshima weapon, around 15 kilotons. But this is an example of what happens if you explode such a weapon. If you want to know about this in more detail, you can go to this web page and set off nuclear weapons at whatever yield you want in whatever place you like. So here's a case with New Delhi, for example. So within this green area, there's a intense burst of radioactive particles and radioactive decay in the radiative explode in the nuclear reactions that caused the explosion. So people die there, not usually instantaneously, but over a week or two. In the next region, buildings made of brick or buildings made of wood, buildings that are not too strong would be blown down and destroyed. Many people would die from the buildings collapsing on them. And in this outer region, which covers the biggest area, fires would be ignited by this bright flash of light. So it's projected here that in this 100 kiloton explosion, and of course, Pakistan claims to have weapons of this size, although it's never tested one, about 614,000 people would die, and perhaps 2 million would be injured. A similar explosion is in Islamabad, might kill 175,000, injure 356, and in Beijing, 356,000 would die. So the variation in these numbers is not because of the weapons, weapons are all the same in this calculation. It's just because of the density of the population in the place where the explosion occurred. And India has very densely populated cities. Okay, so in a war, many more than one weapon would be used. And in this paper, I explored what would happen in a war between India and Pakistan with the arsenals we expect to be present in 2025 or so. So we expect there to be 500 nuclear weapons, 250 in each country. So this picture shows why this is so dangerous. Pakistan is a small country compared to India. India has a much bigger army. There have been cases where there have been terrorist attacks on India by Pakistan, and the Indian army has moved toward the border of Pakistan. Unfortunately, a full-scale war did not occur in most of these cases, and there was some conflict that stopped. And this has happened recently, that there have been provocations like this, as you know better than I do. So if you're a Pakistani, you have to be very concerned about being overrun by India. There have been war games involving retired Indian military generals and Pakistani retired generals and Pakistani and Indian retired politicians who thought about how a war might occur. And this is what they're concerned about, is some provocation in which India moves toward Pakistan and the Pakistanis panic and think that they're going to be overrun and they have to use nuclear weapons. And even if they use the nuclear weapons on Pakistani territory to stop an invading Indian army, the Indian generals say any use of nuclear weapons would cause them to use their nuclear arsenals. And so this is of great concern in the world about a war being triggered accidentally because of the fear of Pakistanis being overrun. So in this imaginary war, we tried to evaluate. Pakistan has 150 weapons. It drops on Indian cities, and India uses 100 weapons against Pakistani cities. Pakistan uses other weapons. It has another 100 against military installations in India outside cities. Some of them don't work. India holds 100 weapons against the fear of China entering the war, and also attacks Indian or Pakistani military installations. So what matters is bombs attacking cities in terms of people being killed and fires starting to cause global problems. So we can compute the number of fatalities and casualties in India and Pakistan from this war. Just to simplify this, if we assume there were 250 weapons that exploded in India, 110 or so million people would die immediately. And another total casualties would be around 170 million people. In Pakistan, the 250 weapons from India would kill about 30 million people, and there'd be 50 million casualties. Fewer people die in Pakistan because it has a very small population compared to India. However, a greater fraction of the Pakistani population dies than of India. You know, this is something less than 10% of the Indian population. But nevertheless, these numbers exceed the number of people who died in the Second World War, which is about 50 million. The death rate around the whole world every year is about 50 million people. So this is 3 times the death rate from natural causes around the world in a year. This would be the first time in world history that more people died in a war than died from natural causes like illness and cancer and heart disease. Okay, so that's the direct effect on India and Pakistan. This image here tries to explain what the global effects of this would be. So we're imagining a war between India and Pakistan with the cities, 250 or so cities burning in India and Pakistan. And this is supposed to be a farmer in Europe or South America or the United States, looking at the maize that he's trying to grow that's died in the field. And he's looking up at the sun, and you can see there's a gray sky here, and the sun is blotted out because of all this smoke in the global atmosphere, which is keeping sunlight from reaching the surface. So the plants get less sunlight, and it's also colder at the surface, which stunts the growth. So we know about this kind of thing from Hiroshima. So this is a picture taken about 3 hours after the nuclear explosion of what's called a pyrocumulus. So this is a fire, cumulus is like a thunderstorm. So this is a thunderstorm created by a fire. And the top of this cloud is reaching altitudes of about 16 kilometers above the surface. So there's probably an injection here of smoke into the stratosphere. After some intense forest fires, we've seen similar injections of smoke. So this is a picture of a forest fire in Canada in 2001. This is a satellite picture. The flattened shape of this tells you it came up and hit the tropopause and couldn't go higher, so it spread out. This is an airplane picture of the same fire. You can see this cloud is full of smoke. This material went into the stratosphere. And we've seen this now in 2017 and in 2020. We've seen huge fires in Canada and Australia that have put smoke into the stratosphere. They put so much smoke in there that satellites have been able to see it for a year, and we've been able to see it perturbing the stratospheric circulation and changing ozone and temperatures there. So we know that the smoke from these fires will rise into the stratosphere. How much smoke is generated by a fire between a war between India and Pakistan? So if there were 250 weapons used, there would be around 10 teragrams, 10 million tons of smoke generated in Pakistan, and around 35 in India from burning cities. And of course, if there's lower yield weapons, not as much smoke is produced. If there's only 15 kiloton weapons used, a lower amount of smoke is produced. We've spent a lot of work, and I'm going to talk to you about another conflict in which only 50 weapons are used. And in total in that one, only about 5 million tons of smoke is produced. So from these kinds of wars, we're talking about 5 to 50 million tons of smoke. For the dinosaurs, we're talking about 15,000 million tons, much more. We know something about how the smoke rises once it reaches the atmosphere. These are some simulations that Pengfei Yu, who's a Chinese scientist now in a Chinese university. He was a student of mine in Colorado, so he went back to home. And these are data from a satellite called Calypso, the black things with crosses, of the rise of this smoke. So this smoke entered the atmosphere at about 12 kilometers from this fire in British Columbia, Canada. And then the sunlight heated the smoke and it rose higher up to about 20 kilometers. And the model that he was using from the National Center for Atmospheric Research is the same model we use to model the wars. And so the smoke rises in these numerical calculations. This has been a prediction since the 1980s. That's the first time we've seen it. So here's a simulation of the smallest war we thought about with only 5 million tons, a war between India and Pakistan. It started on May the 15th. Here we're 10 days later. You can see it spread throughout the entire Northern Hemisphere. It was injected down here below the tropopause, which is the boundary between the lower atmosphere and the stratosphere. And it's risen now to up to about 30 kilometers above the surface at its peak, and all the way up to the mesopause of maybe at 80 kilometers. So this stuff rises to very high altitude. And this matters because once you leave the troposphere, which is commonly 15 kilometers over India in the summertime, once you get above that, it never rains. It does not rain in the stratosphere. So if you have big fires in the troposphere, rain washes out the black carbon in a few weeks. If you go into the stratosphere, the material remains for years. And you can see in this simulation, which includes rainfall removal, that the smoke is spreading rapidly across the Earth. And by a month after the event, it's spread down to Antarctica. There's strong heating in the stratosphere, and the dynamics winds are driven by the heat, the temperature contrast. So this smoke, these numbers here represent optical depths. They're quite small, 0.07, but black carbon has a very great power to stop sunlight. So at the surface, it gets cold. So this is 1,000 years of temperature history. This is a temperature anomaly. And maybe some of you have heard of the hockey stick. So this black curve is a temperature record on the Earth up to about 2000. It turns upward like a hockey stick. And then this imaginary war happens and the temperatures plunge. This is only 5 million tons of smoke. It's colder than any time in the last 1,000 years. It's colder than the Little Ice Age, which is this period of time here, where it's slightly cooler than previously or afterwards. The year without a summer, which Ronald Reagan referred to, is right here in this point. So this is colder than anything we've experienced in 1,000 years of agriculture. But that's not all that happens. The smoke in the stratosphere heats the atmosphere, and the temperatures go up by 30 to 50 degrees centigrade. That changes a lot of reaction rates in the atmosphere and starts to destroy the ozone layer. So what do we see happening to ozone? So this is a typical distribution of ozone across the Earth now. And this little dotted ring marks the ozone hole, where it's been depleted because of industrial pollutants with containing chlorine. And the boundary of the ozone hole is at an ozone column amount of 220 Dobson units, which is about 220 millimeters, or about 2 millimeters of ozone. After this war, this is a small war between India and Pakistan, using about 1/5 of the weapons they expect to have in 2025. The entire Earth is covered with ozone hole levels of ozone. We have no idea what this is due to the Earth. We've never experienced ozone levels like this in human history. The ultraviolet light that could bathe the surface would be very bad for people. You wouldn't be able to go outside, be sunburned in a few minutes. And of course, the biota can't just hide inside. And so we don't know what this would do to plants and animals. Of course, India and Pakistan only have a small fraction of the world's arsenals. The United States and Russia have most of them. There have been agreements to limit them, but they still have outrageous arsenals. A single submarine carrying Trident missiles has the potential to do 1,000 times as much damage as the Hiroshima bombs. There's 100 nuclear weapons on one of these submarines. and each one is at least 10 times more powerful than a Hiroshima bomb. So there's 1,000 times the damage they can do. This is an example of how this can compare to a war between India and Pakistan. So this is the amount of soot produced. Here's this imaginary war between Pakistan and India. A war in 2025 might produce as much as 40 or more million tons of smoke. So this is the India-Pakistan war scenario. Between the United States, Russia, Europe, China, that war might produce more like 150 teragrams. There might be 4,000 or so nuclear explosions just from the strategic deployed weapons that exist. Treaties between military people and politicians don't pay any attention to this. They only care that the military is assured that they can destroy a certain fraction of the enemy's cities. So they want to bomb each city with 100,000 people with 10 nuclear weapons. That's what they care about. They don't care that the smoke might then damage or even extinct a large fraction of the human population. So if there were a war between Russia and the United States, Europe, China, the temperatures are predicted to drop about 10 degrees centigrade from normal globally. The last ice age was only about 5 degrees cooler. So these are colder temperatures than in the last ice age. An India-Pakistan war with only 50 nuclear weapons on each side is this little red blip up there. So it's much colder than that. What does this do to agriculture? So this is an example from the Ukraine, the red basket of Europe. Similar things happen in Iowa and the middle of the United States. So in a normal year, this is temperature here and time in years. In a normal year, it gets cold in the winter and it's warm in the summer, and it's cold in the winter and warm in the summer. After this imaginary nuclear war between the United States and Russia, it starts to warm up. The war occurs, temperatures immediately drop below freezing. They stay freezing as the winter approaches. They stay freezing as the next summer comes. They stay freezing the next winter. They barely get above freezing in the second summer following. Nothing will grow at mid-latitudes. This will cause mass starvation. So our group includes not only climate people that are doing these kinds of calculations, but also agricultural people. So this is an example of our calculations that will be published soon of the caloric loss, the number of calories that are lost because of agricultural failure around the world in various countries. And it depends a little bit on whether you allow livestock like cattle to continue to exist and you feed them grain, or whether you don't let the livestock continue and you eat the grain instead of feeding it to the animals. So here's a 5 teragram war. Excuse me. 13% losses in China, North Korea 12%, modest losses. A war between India and Pakistan with 100 kiloton weapons like we expect in 2025. China loses 80% of its calories. France 30%, North Korea 98%, 91% in Russia, 76% in the United States. 150 teragram war between the United States and Russia. Most countries are losing 99%, 100% of their caloric intake. There is a pattern here, which you can see that India wouldn't be too badly damaged from the global effects, but this doesn't reflect all the people that were killed by the nuclear weapons, all the radioactivity that spread around the country. But the pattern here is that if you live in a high latitude country, like China, it gets colder, it damages your crops. If you live in a tropical country like Israel, it's already pretty warm. So if you cool it off a little bit, it's easier to grow crops. So tropical countries are not damaged quite as much as the ones at mid latitude. How many people might survive this? So this is a percentage of the population alive at the end of the second year. And this is calculated by assuming that a certain caloric input is needed to save lives. You give some fraction of your population those calories, and the rest of your population, you give them nothing to eat. So this is the most optimistic survival situation. So I don't want to dwell on this because of the time we have left. But if we go down here to the Russia-United States war, 1% of the population will survive in countries marked by this brownish color here. So only 1% of the population in Russia and China would survive, about the same in Canada, 25% or less in the United States and various parts of Africa, less than half of the people in India. Some places would not be so bad, Australia, for example. So this would devastate the population around the Earth. People have estimated that only a few hundred million people would survive war between the United States and Russia and Europe and China. It's estimated that this war here, with the 50 weapons on each side from India and Pakistan, would probably kill about 1 billion people. So we're losing 1 billion people worldwide from this, and possibly something in the 20 to 50 million range in India and Pakistan. So this is a devastating impact on world civilization from a war like this. Okay, so now let's try to compare the dinosaurs, a Pakistan-India war, and a US-Russia war involving Europe also and China. So this is the amount of sunlight reaching the ground through the smoke as a function of time. And on these graphs, the dinosaur case is a black curve, the US-Russia war is a red curve, and the Pakistan-India war is a blue curve. So what happens in the case of the dinosaurs is you take all the smoke that's in that boundary layer, we know that smoke, we put it back into the atmosphere. The sunlight is less than 1% reaching the ground for about 2 years after this event. Photosynthesis needs more light than 1%. This would cause extinctions in the oceans because of starvation. After the US-Russia war, only about 10% of the light reaches the ground. This would not cause photosynthesis to stop, but of course it would certainly be bad for crops. Well, most of the light still reaches the ground after a Pakistan-India war. I think this is a 30 teragram case. Loss of light will cause the temperatures to drop. After the dinosaur case, they probably dropped about 15 degrees, which caused a global average temperature to be at freezing. In the US-Russia case, -9 degrees, and in the India-Pakistan war, -3. All of these temperature drops were devastating to agriculture. Precipitation would fall because it's colder at the surface. So for the dinosaur case, probably 80% of the precipitation was lost. US-Russia, 60%, India-Pakistan, about 20% of the precipitation is lost. In all these cases, the monsoons fail. And so there's quite a bit of loss in the tropics of the precipitation because the intertropical convergence zone no longer is full of clouds and rain. The ozone layer is destroyed in all these cases. You lose 80% of it in the case when the dinosaurs went extinct, 70% in the US-Russia war, and about 40 or 50% in the Pakistan-India war. So what does all this mean? It's very difficult to tell. We need additional scientists to examine this problem. We need scientists around the world to examine this problem, not just in the United States. That's how scientists had an effect in the 1980s. Russian scientists advised Russia. American scientists advised the United States. We need people to do these calculations besides our small group. But let's look at it. So here's amount of smoke injected as far as we can tell. And you can see there's 1, 2, 3, 4, 5, 6 orders of magnitude here, a factor of 1 million. So interesting fires, fires in forest have been injecting about 0.01 teragrams of smoke from these Canadian and Australian fires. After the dinosaurs, 1 million times as much smoke was injected, about 15,000 teragrams of smoke. We think in an India-Pakistan war, somewhere between 5 and 50 teragrams of smoke will be produced, which would be very bad for agriculture in many countries around the world. And in a US-Russia-Europe war, about 100 or 150 teragrams of smoke would be produced. And at mid-latitudes, we think it would look like this for several years. So right now, we can't stop an asteroid impact, but we're working on it. You probably think this is a little picture, but this is the United States imagination of how you stop a war, which you send cowboys up and they blow up asteroids, which is not the scientific community taking care of this problem. It remains to be seen if we can prevent a nuclear conflict and global starvation, but history shows that you, the world scientific community, can help eliminate this problem. And just to summarize this, for the India-Pakistan War, probably 50 to 150 million people would be killed by what's called assured destruction. We're fairly confident of these numbers. Reduced temperatures to the lowest level in 1,000 years, shortening growing seasons, reduced rainfall in the tropics, destruction of the ozone layer, large losses of agricultural production would result in global starvation. These are some of the people who've been working on this problem. Thank you very much.
Thank you, sir, for such an insightful lecture. I'm sure that I'm speaking on behalf of the entire audience watching us right now, that you have positively revealed groundbreaking thoughts and promising ideas while instilling a new perspective in our lives. We'll now begin with the Q&A session to answer a few of our audience questions. The first one goes as, some scientists believe that asteroids and comets will bring more new resources to our planet if the hitting of the asteroids is managed properly. What are your views on this? Is this practically possible?
Yes, well, the idea there is that a large asteroid could be worth trillions of dollars because it contains all sorts of valuable minerals, and some of them are very highly purified, and so that you don't need to, for example, an iron meteorite is mostly iron, and so you don't have to go dig holes in the ground and separate the iron from other minerals. And so the challenge, of course, is to bring these minerals to the surface of the Earth in a controlled fashion and in an economically viable fashion. And there are definitely people in various countries out there who think you could do this. And, more practically in the near future, there are people who think that you can mine things on the moon and Mars to sustain civilizations on the moon and Mars. Very optimistic people like Elon Musk thinks he's going to land people on the moon in the next few years and on Mars by 2025 and start colonies of people living there. I don't think I'm going to volunteer for that. I'm too old for the excitement, number one, but also I don't think you're going to come back from this thing because I don't think we're ready to do this. But nevertheless, that's the first places we will be mining extraterrestrial resources. I have, for example, foreign students who've thrown spent rocket boosters at the moon, collided those objects with the moon in order to blow material off the moon so that they could spectroscopically analyze it and see how much water is there. Because obviously the first thing we need to survive is water, and there is water on the moon.
That was quite insightful. For the last question we have, what is your message for the students watching this stream today?
What's my advice for students? Well, I think there's lots of different kinds of advice for students. I mean, the most important thing is to do something that you're passionate about because it's a lot of work to do science. And so you have to have a lot of determination, to continue to do it. And of course, there are many famous Indian scientists, won Nobel Prizes and made huge advances. A lot of the work I do depend on radiative transfer work that Chandrasekhar developed, for example. And I've done other things that Raman invented, for example, both famous Indian scientists. So, you have to do something that's interesting to you and you're very passionate about, and you're going to pursue, very hard over a long period of time. I published my first paper in 1973. So I've been writing papers for almost 50 years at a pretty constant rate. So do something you like and that you're interested in. And, obviously there are barriers to Indian scientists and breaking through into the rest of the world. And so that's an issue to overcome. There are many Indian scientists, particularly involved in computer technology and other fields like that. So I see in my university, for example, that older Chinese scientists, or now we have one Indian on our faculty and 2 or 3 people from China. And, that those people understand their native countries well enough to know how to bring students to the United States from their native countries. And so that's a good channel to advance your education that way. I'm sure lots of Indian students go to Britain because there's a long-standing interaction there. And, so Americans are not very well educated about India. American professors don't know how to evaluate Indian students. I get lots of letters from Indian students wanting to know about American universities, and I don't know how to advise them. But if you contact someone who knows about India, you're much more likely to find a path that way. My own son just finished a master's degree at the University of London. So people, even in the United States, want to go to other countries to learn about things. I think in the upcoming Chinese Olympics, there's an American skier who's skiing for China, which is somewhat controversial. I have several students who are faculty members in China now who came to the United States and then went back home to China. So I think as the world advances, that there'll be more and more of this international exchange. And of course, there's nothing wrong with Indian universities. India has a very strong university program. And, there are many famous Indian scientists contributing to almost every field of science you can think of. So I think you should be proud of your country and its intellectual contributions. And you can also work on these same problems. You can get the same codes that we use. The National Center for Atmospheric Research distributes its codes worldwide. If you want to work on these kinds of problems, you could get these models. And of course, they're native Indian meteorological and climate models as well. And I think it would be wise to think about the political structure in India and whether they need advice about nuclear conflicts. For example, in 2020, there was a interaction going on between Pakistan and India where each country bombed each other, coming out of the problems in Kashmir. So it's most unfortunate that India and Pakistan can't solve the Kashmir problem politically. It continues to fester and continues to cause problems. My 2019 paper explaining the number of casualties that might occur from a nuclear war between India and Pakistan. I wouldn't say it was quoted exactly, but the president of Pakistan and Kashmir referred to the idea as a reason why there should not be a nuclear conflict between Pakistan and India over the change in the Indian constitutions relative to Kashmir, for example. So the Indian politicians and Pakistani politicians need advice from you. about political problems that they face. And it's not just nuclear wars, of course, it's global warming, how to produce energy in India, and all sorts of problems like that.
Your answer has left us filled with enthusiasm. I'm sure the audience learned something new from this answer. This
Well,
has
thank you.
been an amazing session. We were able to learn a lot about what we tend to ignore about our generation and environment. We are simply elated you could join us today. It has inspired us to work towards catalyzing your initiative of making the world a better place. Thank you so much, sir. Also,
Thank you for inviting me.
thank you to our audience for tuning in. We hope you all enjoyed the session. I am Harshada Pavane signing off. And until next time, this is Technovanza VJTI.
So,
Okay.